Good morning, welcome back to our physics classes. So we have completed the chapter thermodynamics, the concept of thermodynamics, unit of thermodynamics, and now we are going to start with the last session. That means the last topic in the syllabus, last unit in the syllabus, that is waves and oscillations. See, these waves and oscillations are coming in a particular unit. But in your textbook, it is given in different chapters. But you remember all these are coming under waves and oscillations. Okay, so Unit 10, the waves and oscillations and waves. So we are starting this chapter with the concept of simple harmonic motion. Your chapter number 23, that is simple harmonic motion. See, from this unit, oscillations and waves, some topics are removed, and all the chapters are, according to the textbook I am saying, so all the chapters and all the topics given in your textbook as under oscillations and waves are not there in the syllabus, and what are the removed portions that I will discuss when we are coming to that topic. So while preparing this chapter, you just follow the revised syllabus. Okay, anyhow, we are starting with the chapter simple harmonic motion. So before defining simple harmonic motion, we are saying that it is oscillations. It is a part of oscillations. So oscillation is a special kind of movement in physics, and it's a part of periodic motion. What do you mean by a periodic motion? All these terms you are familiar with from your lower classes. Anyhow, we are just revising the terms periodic motion. What is periodic motion? Periodic motion is a type of movements in physics which is repeating after a certain interval of time. So the simplest periodic motion that you are knowing is, what is that? Yes, that's your heartbeat. So heartbeat is a periodic motion. It repeats after a certain interval of time, and it has its own frequency, and these movements are having some disturbance from a mean position, and that is known as the displacement, and the maximum displacement is known as the amplitude, and time taken for a complete periodic motion is called time period, and the number of repetitions per second unit time, that is known as the frequency of that periodic motion. All these matters you are knowing. And periodic motions can be expressed mathematically with some functions, and these functions are also repeating after a certain interval of time, and that functions are called periodic functions. Periodic functions are familiar to you, and you know values of sine function and cosine function. Better examples: sine function starting from 0, when sine 0 is 0, sine 90 is 1, sine 180 is 0, sine 270 is -1, and sine 360 is again 0. So it completes one full variation. Again, sine 90, 360 plus 90, that will become +1, then 0, -1, 0, that repeats. So sine function, cosine function, cos 0 is +1, 90 is 0, 180 is -1, 270 is 0, 360 is +1 again. You can see the variation of that sine function, cosine function, that repeats after certain interval of time. What the time interval? The 2 pi radian or 360 degree. After 360 degree, it is repeating. Okay, you know that. So that kind of functions are called periodic function. Mathematically, we can say that they are periodic functions. An oscillatory motion is a kind of periodic motion. It repeats after a certain interval of time. So what do you mean by oscillatory motion? Suppose a body or a particle moves about a fixed point into and fro within a certain interval of time, and the movement is repeating after a certain interval of time. So we can say that it is a periodic oscillatory motion. Peculiar point regarding periodic motion, oscillatory motion, is it is moving about a fixed point, and that point is known as the equilibrium point or fixed point, means zero amplitude, whatever you can call it as. And above that point, it makes up and down or to and fro. Means up and down is also to and fro motion, or it is horizontal direction or vertical direction, whatever it is. So anyhow, about a fixed point, to and fro motion is undergoing. Such kind of a motion is called oscillatory motion. You use the term vibration, also the same concept. That means suppose you are having a scale and you are keeping the scale at the edge of the table and you are just disturbing it, it will make vibrations. Is it? You call it as vibration, not as oscillation. And if you are having a simple pendulum and you are just displacing it, it will make to and fro motion about its particular point, fixed point, equilibrium point. And that movement you call as not vibration, but it is oscillation. What the difference is? Oscillatory motion and vibratory motion both are similar. In the sense they are different that from the equilibrium, if the displacement is comparatively larger, then you can call it as oscillation. And if the displacement from the equilibrium is comparatively less, then you can call that kind of motion is to and fro motion again. To and fro motion is called vibratory motion. So depending upon the amplitude. If amplitude is more, comparatively more, then that is oscillation. And if the amplitude is comparatively less, then that is vibration. Again, both are about a fixed point and it's a to and fro motion. Remember that. Anyhow, our topic is all these matters till now you are familiar with, and we are starting our concept with the simple harmonic motion. So any function, any oscillatory motion that can be expressed in terms of a harmonic function. I already told you what is a periodic function, harmonic function. A harmonic function that is known as a harmonic motion. See, again, our sine function and cosine functions are harmonic motions or harmonic functions, and very easily you can define them. Any oscillatory motion that can be expressed in terms of a sine function or a cosine function, that can be considered as an harmonic oscillatory motion. And that oscillatory motion is having one same amplitude and one frequency, then you can call it as a simple harmonic motion. Harmonic motion can be of different amplitude and different frequency, but it is having one same fixed amplitude and single frequency, then you can call it as a simple harmonic motion. Okay, so any oscillatory motion that can be expressed in terms of sine function or cosine function can be considered as an simple harmonic motion. Sine function, cosine functions are simple harmonic functions. And we can see that when you are considering a simple harmonic motion, when suppose a system is there and that system is in equilibrium and you are disturbing that towards the left, it will make movements to and fro about that equilibrium point. For example, your simple pendulum, it will make to and fro motion about the fixed point. And when you are displacing towards the left, it starts movement towards its right. That means the movement is always opposite to the displacement. The movement is always opposite to the displacement. And we can say that simple harmonic motion, the force acting on the system will be always opposite to displacement, and again it is proportional also. That means F proportional to minus x. F proportional to minus x. That means the restoring force acting on a system is directly proportional and opposite to the displacement happened there. Then you can say that is a simple harmonic motion. That is again another example, another way for defining simple harmonic oscillation. Simple harmonic oscillation. Simply we can say that any movement which can be expressed in terms of a sine function or a cosine function, you can call that as a simple harmonic motion. So how you can express or how you can give an example for a simple harmonic motion? Very simply you can explain the concept of simple harmonic motion with an example. So listen here. So you are having a particle which is at a point A. A particle is at a point A which is at a distance r from the fixed point C. Okay? It is moving in such a way keeping the constant distance from the point C. It is moving in such a way the distance from the C is kept constant. So what will be the path of that particle? That will be a circular path. Okay, so in simple words we can say that it is undergoing a circular path in anti-clockwise direction. It is moving a circular motion, it is having a circular motion in the anti-clockwise direction. So suppose it is rotating or moving with an angular velocity omega. After a time t, you can have that point in particle, suppose this is taken as P1, particle is at P2 making an angle omega theta. Okay, so you can have our x-axis and y-axis, and the coordinate origin will be at the center. So this is x dash axis, and this is your y dash axis. So at any instant, you can have the coordinates of the position of the particle. See, this is x2 and this is y2. First one, this is x1 and y1 should be 0 because it is at the x-axis. And when the particle is here, this is the point y3 and x3 is equal to 0 since it is along the y-axis. Here you can have that point that is P4, this is P3. Then the coordinates are see x4 and y4. Now the particle is here at P5, x5 and again 0 because it is along the x-axis. And then when you are having the point here P6, then its x coordinate is x6 and y6. Is it? When it is at the point y dash, at this point P7, this is y7, but again it is x equal to 0 because it is again along the y-axis. Now it is here, then see, this is P8, that means y8 and this point will be x8. Getting confused? See, you see the x coordinate only. First of all, you see the x coordinate only. So, x coordinate, suppose this radius is taken as, you are taken as a radius is taken as small a. So, when you are having along the x axis, that is at the point P1, you can say that x1 is equal to a. X1 is equal to at the point P1, x1 equal to a and y1 equal to c. At P2, you can say x2 is equal to a cos omega t and y2 is equal to a sin omega t. You can take it as T2, T2. At time T1, T2 like that. Then at P3, you can say x3 is equal to a cos omega 3, that will become 0. And y3 is equal to a. Is it? Then P4 you can have x4 is equal to again a cos omega t4 and y4 is equal to a sin omega t4. Then at the point P5 x5 is equal to a and y5 equal to 0. Then P6 x6 is equal to a cos omega t6 and y6 is equal to a sin omega t6. Then at P7 x7 equal to 0 and y7 is equal to a. Is it? Then again x8 P8 is equal to a cos omega t 8 and y is equal to a sin omega t 8. Again at 9 what happened? It again coming back to the same point p1, so that will result in the same x1 equal to, x10 is x9 equal to a and y9 equal to 0. Okay, now at this point p1 a is positive and p5 a is negative, is it? And x6 also, x4 also negative. See, x4 you can get it as negative towards the left of the origin, that is negative. x6 is also negative. Then x8 is positive and p2 is also positive. Similarly, you can have the same argument for y also. So you are focusing on x only now. You can see that initially x is maximum. As the particle moving in anti-clockwise direction, as it makes 90 degree from the origin, x coordinate will become 0. Then it grows in the negative direction and it goes to maximum. Again it is coming back to origin and grows to the positive maximum. So when you are taking the movement of the foot of this particle towards the x direction, you can say that it is moving from plus a to minus a, crossing the 0 two times. From plus a, it is moving down and again coming back to the. Okay, so it follows a cosine function. It follows a cosine function. And when you are calculating about the y direction, you can say that that is following a sine function. That means initially it is 0, growing to a, then again 0, growing to minus a and again coming to 0. So which can be taken as, x can be taken as a cos omega t and y is equal to a sin omega t. What it says, x is the instantaneous displacement along the x direction at any instant. Y is the displacement along the y direction at any instant. And both are growing from positive maximum to negative maximum and again moving to positive and negative, crossing the equilibrium point 0, which means x and y are following a sine function or a cosine function. What it means, sine function and cosine functions are harmonic, simple harmonic functions. So movement of x and movement of y, that means displacement along x direction and displacement along y direction, are following a sine function or a cosine function. So the x variation and y variations are simple harmonic variations. So we can say that the circulatory motion is an example for simple harmonic motion. Why? Because the movement of a particle along the circumference, then the displacement happening to that particle along x direction and y direction, you can express in terms of simple harmonic functions. That is the definition for a simple harmonic motion. Any movement that can be expressed, movement expression means displacement expression. How you can define that movement? How you can define the movement? You can the way how you are defining the displacement. Why you are calling it as a rotatory motion? Because it is the path is rotating in a circular path. Why it is a linear motion? That means it is moving along one direction only. How it is a planar motion? It is moving in a plane. That means how you can define the movement? The way you can define its displacement. In the same sense, circular motion, how you can describe with the displacement happening to the particle in x direction, y direction. That can be easily shown with the help of or explained with the help of a sine function or a cosine function. X direction you can express with a cos function and y direction you can express with a sine function. So we can say that it is, a circular motion can be explained with the help of sine function or cosine function. Both are simple harmonic functions. So we can say that circular movement is a simple harmonic motion. So it is simple harmonic motion. So in simple harmonic motion, displacement along x direction you can express as a cos omega t and y is equal to a sin omega t. That means initially the particle is starting from x direction. Suppose initially it is not along the x direction, which means suppose you are having a circular path, its x direction, y directions are there. Initially the particle is here. That means initially it is making an angle phi there. From the at a time t, it may derives an equation omega t. So the displacement from the x direction will be x is equal to a cos omega t plus phi. Because phi displacement is angular displacement is already there, and that is known as the epoch. That is known as epoch, and that is known as the initial phase angle. Initial phase. In most probable cases, that epoch will be 0. That means we are considering the particle starting its motion from the x direction. In some particular movement, suppose it is saying that already it is made a angle phi, and after that only you started your movement, observations. So in that case, epoch will be the initial phase angle, that is phi. In that sense, you can say, generalize, you can say x is equal to a cos omega t plus phi and y is equal to a sin omega t plus phi. Where phi is epoch the initial phase. Most in cases, phi will be 0. Anyhow, in general, x displacement of a simple harmonic motion can be expressed as a cos omega t plus phi and y is equal to a sin omega t plus phi. Okay. So that is the displacement of an SHM. Displacement of an SHM is x equal to a cos omega t, y is equal to a sin omega t. Generally, we are taking the y oscillation. So y is equal to a sin omega t plus phi. You can say that is a sin omega t since phi is equal to 0. Initial phase angle is 0. So when you are taking the derivative of y with respect to t, you will get the velocity of displacement. SHM. So v is equal to dy by dt is equal to a omega cos omega t. A omega sin omega t. Differential of sin omega t is cos omega t. So you can say that dy by dt will become a omega cos omega t. And you know cos theta is equal to root of 1 minus sin square theta. So you can say that it is a omega into root of 1 minus sin square omega t. And when you are taking this a to the square root, it will become omega into root of a square minus a square sin square omega t. What is a sin omega t? A sin omega t is y. So you can express it as omega root of a square minus y square. What is this? This is the velocity of SHM. Velocity of SHM. Okay. Now, when you are defining a cos omega t as a velocity, if you are taking the derivative of velocity, what you will get? You will get the acceleration. So, dv by dt is equal to d by dt of a omega cos omega t. That will become a into omega into sin omega t with a negative sign. Because d by dt of cos omega t, that is derivative of cos omega t is minus omega sin omega t. Okay. So that will become minus omega square a sin omega t. A of sin omega t is y. So that is minus omega square y. What is this dv by dt? That is acceleration. So acceleration is equal to minus omega square y. What is this omega? Omega is the angular velocity. If it is moving with constant angular velocity, then a proportional to minus y. That is a proportional to minus y. What is that? This is acceleration. Acceleration is directly proportional to minus y. When you are multiplying with the mass, you will get force. And force directly proportional to minus y. Mass is constant. If you are multiplying with that constant again, right hand side no problem, that will be a constant. So f is equal to f proportional to, or f is equal to minus ky. What it says, f is proportional to minus y. That I told you, another way of expressing a simple harmonic motion, that means force is directly proportional to displacement acting in the opposite directions. So F is equal to minus Ay, that is another definition for your simple harmonic motion, that is F, the restoring force acting will be proportional to the displacement acting in the opposite direction. That is F is equal to minus Ky. So you have the how you can express the simple harmonic motion. It's displacement, velocity and acceleration, and equation for simple harmonic motion, that is F equal to minus m omega square y. See, A is equal to minus omega square y, A is equal to minus omega square y is equal to m, A is equal to minus m omega square y. This m omega square is replaced by k, so F equal to minus k y. Simple. Okay, so that is simple harmonic motion and its basic properties. Okay, so that's all for today, and we will meet in the next class.